much, David. We have time for one question. Well, David will be here during the break, so I think we're going to go on and introduce the next speaker. Thank you very much.
Umit, would you like to use the microphone?
Yeah, that might be it. It's my great pleasure to introduce our next speaker, Professor Umit Ozkan from the Ohio State University, the Department of Chemical Engineering. And I would like to highlight again that there was a mistake. The authors should read Paul Mather, Elizabeth Bibiger, and Umit Ozkan. The presentation will be on nanostructure, carbon nanotubes, catalysts for oxygen reduction reaction in PEM, and also direct methanol fuel cells.
Probably the mic is not working, so I'll try to speak a little louder and hopefully my voice will carry. I think we have the blocking the view. The title of my talk is Nanostructure Carbon Nitrogen Catalyst for Oxygen Reduction Reaction in PEM Fuel Cells. And hopefully through this talk, I will try to make the connection between the world of catalysis and the world of fuel cells. My co-authors are Paul Mather, who was a former PhD student who really started this project, and Elizabeth Bidinger, who is in the audience, and she is going to give a poster presentation later in the afternoon about the more recent results. I will focus mostly on the earlier phase of the study. So what we're focusing on is proton exchange membrane fuel cells, also referred as polymer electrolyte membrane fuel cells. We just say PEM. These are using acidic electrolytes, which is a polymer membrane. Hydrogen ions pass through the electrolyte. They're formed in the anode. They go through the electrolyte, and then they combine with the oxygen on the cathode, form water, and the electrons that are generated are sent through an external current, external circuit, so we get the current. The fuel is pure hydrogen or methanol, and the operation temperature is low. It is less than 80 degrees centigrade. And of course, this low temperature is really the cause of many catalysis-related issues that we are facing, because the temperature is so low, the kinetics is quite slow. So the reactions we're looking at is the proton formation on the anode and the oxygen reduction on the cathode, and per 1 molecule of oxygen reacted, we're dealing with 4 electrons. And this is the reaction that we're focusing on. So our research is focusing on the cathode side. Now, if we look at the current technology, we see that current technology is really relying on platinum electrodes on both sides. We have issues with the anode poisoning because of CO concentrations, even very low CO on the in the hydrogen streams. Membrane hydration is required, and then the cathode performance is still limited because the temperature really makes the kinetics very slow, and long-term stability still is one of the limitations for this technology. Now, if we look at the current technology on the cathode side, as I've said earlier, platinum is the catalyst. Obviously, the cost and feasibility are very important. Again, if we look at the required platinum, if we try to convert a good portion of the cars to PEM fuel cell operated cars, we may replace dependence on foreign oil by dependence on foreign platinum. So, and the platinum alloy is being used for improved stability, especially on the anode side. It is being doped with Nafion, which is the polymer electrolyte. Platinum utilization is quite low. And if you look at the voltage versus current diagram, typical diagram from a PEM fuel cell, as you can see, as we start drawing current, the voltage drops as expected. But if you look at this first sharp drop, that's really the kinetic controlled regime. And this is because of the slow kinetics at the cathode side. In here, we have the resistance-related ohmic losses, and then if you go further in the higher currents, we start seeing potential losses because of mass transfer limitations. So the challenge is really bringing platinum, electrons, oxygen really together, and also have high both proton conductivity and electron conductivity. Another problem with platinum is the fact that it is active for direct methanol oxidation, which creates a problem with direct methanol fuel cells, because methanol can cross through the polymer membrane, and then if we are using platinum as an electrolyte, as a catalyst on the cathode side, it oxidizes and really causes further potential losses. So there have been, of course, quite a few studies looking at alternatives to platinum. One of the earlier ideas was looking into organic macrocycles, and some of these were really nature-inspired ideas, looking at molecules like hemoglobin, where iron is a central site. Some of these organic macrocycles like these have been tried in fuel cell atmospheres, environments, although they have some initial activity. The initial activity degenerates very quickly. It has also, some people have tried heat-treated macrocycles, and they have seen that the activity actually improved. And more recently, iron, nitrogen, carbon-containing compounds going through a heat treatment have been used with some success as possible cathode catalysts. Now, when we look at these iron, nitrogen, carbon-containing compounds, there's an active site debate going on. What is the role of iron? Is iron really part of an active center, active site, or is it simply catalyzing the formation of the active site? And one of the initial questions we wanted to answer in our research was this question. Again, if you look at the literature, there is perhaps evidence on both sides that iron is part of the active sites. For example, the activity of iron centers in macrocycles is well established. Presence of iron improves activity. And also some people have reported phenanthrene type sites detected in heat-treated materials. But there's also evidence on the other side that iron is not part of the active sites. The fact that most macrocycle type sites should decompose into metal particles when they are treated above 600 degrees centigrade. It has also been shown that if we remove iron, actually we may improve activity, and samples with very, very low iron concentrations can still show activity after some pyrolysis treatments. So in our early research, we started out using Vulcan carbon as a support material, which is also the support used for platinum, doping it with some metals, and then going through a acetonitrile decomposition or a pyrolysis treatment. In this case, we are saturating nitrogen with acetonitrile and then exposing the Vulcan carbon to this environment at 900 degrees centigrade. This is really a deposition of the carbon nanostructures. And we looked at the effect of time, temperature, and atmosphere on the treatment. Now, if we look at the carbon deposition process using thermogrametric analysis, what we see is that if we look at the weight gain, and weight gain really represents the carbon deposition on the surface, when we have Vulcan carbon doped with iron, there's a faster weight gain. So we have more carbon deposition, carbon nanostructure growth on the support materials. If we look at the surface area and pore volume of these materials, For any, going backwards, for any weight gain, if we look at them, the iron-containing Vulcan carbon allows carbon structures to grow with higher surface areas. When we look at the pore size distribution, the red curve represents the carbon structures grown on iron-doped Vulcan carbon. What we see here is a pore size around 4 nanometers, and we don't really see it on carbon structures grown on pure Vulcan carbon or nickel-containing Vulcan carbon. Now, if we look at the X-ray diffraction, and we have an in situ X-ray diffraction system where we can go from cryogenic temperatures to 1200 degrees centigrade, pretty much in any atmosphere that we want. Here is the X-ray diffraction pattern for Vulcan carbon. As we go through these materials which have gone through the acetonitrile treatment, we end up with smaller graphite plane in the carbon structures. These are structures grown during the acetonitrile treatment. And this shift is also seen in multi-walled carbon nanotubes. And if we have iron present on the support, this shift appears after shorter times. As you can see here, here's the Vulcan carbon, and we're getting closer to the despacing that's seen in multiple nanotubes. Raman spectroscopy, again, has typical bands for D and G bands. They are referred as, they refer the order limits of these materials. And looking at these carbon structures, we see both of the bands. The differences between the catalysts are not really very noticeable, but in terms of the identification of the graphite structures, we clearly are growing these nanostructured carbon materials. Now, we looked at the oxidation behavior of these materials, how easily these materials get oxidized. Again, we are using a GCMS combined with a TGA system. And if we look at the effluent from the temperature program oxidation experiment, here's the Vulcan carbon. The oxidation is starting around 600 degrees centigrade. And here is the carbon structures which are grown as a result of the acetonitrile pyrolysis. And as you can see, the oxidation starts much earlier. So whatever we have in these materials clearly is catalyzing the oxidation of carbon. But we also see very clearly nitrogen oxide coming from these materials, showing that we have significant levels of nitrogen in these carbon nanostructures. Now, we have looked at the activity of these materials using electrochemical measurements. We are using a half-cell method. We are using either a rotating disc electrode or more recently rotating ring disc electrode. And these are relatively easy experiments compared to putting together a membrane electrode assembly each time you wanted to test a catalyst. We have the reference electrode, a counter electrode, and here's the working electrode at the tip of which we place the catalyst that we want to test. And the electrolyte in this case is an acidic electrolyte mimicking the behavior of naphthalene, which is the polymeric electrolyte that is used in PEM fuel cells. Using rotating ring disc electrode system, it is also possible to get the selectivity information in addition to the activity information, because if we look at the reaction that the oxygen can go through, there are really two possibilities. One is the incomplete oxidation, oxygen reduction, giving hydrogen peroxide, which really gives us a net electron loss, and then the complete oxygen reduction, which is what we want. So with the rotating ring disc system, we are able to differentiate between these two reactions and get a selectivity value for the electron oxygen reduction reaction. Now, this is a typical voltammogram from the half-cell setup that I just showed. Again, if you look at the literature, there are different ways of comparing the activity of these catalysts. Some people look at the voltage at the 0 RPM and report the maximum at which the voltage at which the maximum takes place. And some people look at the baseline separation. In our earlier work, we were mostly reporting the position where the peak takes place, and the closer we are to the theoretical value of 1.2 volts, the more active the catalyst. And if we do some quick comparison, here's commercial platinum on Vulcan carbon. This is a commercial catalyst. Here's one of the carbon nanostructures that we generated. Again, it is not as active as commercial platinum, but still it has very significant oxygen reduction activity. Another important thing to note in this diagram is that here's the Vulcan carbon. Obviously, it has very, very low activity. But here's Vulcan carbon, which doesn't have any iron, but it has gone through the acetonitrile treatment. So clearly, by acetonitrile treatment, even Vulcan carbon is gaining some significant level of activity. What type of species do we have? We already established that we have nitrogen species. And if we look at the nitrogen content of these carbon-nitrogen nanostructures, we see that there is some correlation between the reduction peak voltage, and again, the higher this is, the more active the catalyst. So there's almost a linear correlation. However, the catalysts which are prepared over iron-containing supports have almost a step function increase in activity. Now, again, X-ray electron spectroscopy is able to differentiate between different nitrogen species that can be formed over these graphite materials. For example, we could have pyridinic nitrogen, which can only take place at the edge sites, or we can have quaternary nitrogen, which can only be seen on the basal plane of the graphite. And these different nitrogen species can be differentiated through XPS because they give binding energies different enough. And if we look at the a typical sample, in this case, nitrogen 1s region, carbon structures grown on Vulcan carbon, we are able to differentiate the quaternary nitrogen and pyridinic nitrogen. This one is, at this point, we're suspecting that it may be an oxidized form of the pyridinic nitrogen. And again, if we compare the two materials which are grown on Vulcan carbon only versus iron-containing Vulcan carbon, there's a definite increase in the pyridinic nitrogen content, which is very easy to see. And this is the catalyst that gave us the higher oxygen reduction reaction activity. Now again, if you look at the literature, carbon fiber growth over metal particles is a well-studied phenomenon. And growth usually takes place through carbon dissolution and migration into the metal particle, and then through the formation of a carbide intermediate. And again, if we look at the different nanostructures, carbon nanostructures that we form, we also see that there are differences in the way the edge plane is exposed. For example, you can have you can have the multi-walled nanotubes, and you primarily only have basal plane exposure because it's almost like sheets of paper wrapped around. If we look at structures like the herringbone, as you can see, we have much more of the edge plane being exposed. Or stacked platelets is another example, or ribbons. We also see sometimes these nano onions, and again, there is only basal plane exposure in these materials. So what do these materials look like using transmission electron microscopy? In this case, we were using a Techne system. Here is carbon nanostructures grown on iron-containing Vulcan carbon support after acetonitrile treatment. You can clearly see the carbon fiber growth, and at the tip of these, you can see the metal particles. In this case, these are the iron particles. And here is a single fiber, and if you look closely, and maybe if I draw the lines, there are basically graphite planes, the graphitic planes, are at an angle to the axis of the fiber. So as you can see here, the graphite planes are ending at an angle, and all of these are exposed edge planes. And also, if we look at the tip of one of these fibers, you can clearly see the pear-shaped iron particle at the tip of the fiber. If we look at structures which are grown on nickel-containing Vulcan carbon, we don't really see the fibers. We have mostly these onion-type materials with very little edge plane exposure. And this is pure Vulcan carbon after acetonitrile treatment. Again, as you can see, we have mostly these nano onions. Now again, there is debate, of course, about what the active site could be. So at this point, we were still faced with the question of, is really iron playing a role? Because as I said earlier, there is evidence reported in the literature about the presence of phenanthroline type sites which could have oxidation reduction activity. And these authors think that nitrogen could be stabilizing or anchoring the iron. But there are also other possibilities. For example, presence of pyridinic nitrogen could be improving the absorption of oxygen, or it could be changing the electron donation capability of carbon, especially at the edge planes. Now, the question we have not answered was, what is the role of iron? Because although even the Vulcan carbon, which didn't have any iron, showed significant activity after acetonitrile pyrolysis, Vulcan carbon still has some impurities in the form of iron, about 70 ppm. So we really couldn't be sure. So we said, well, let's try to prepare some support which would be really free of any metal contamination. And we prepared some alumina support using a sol gel technique with very, very low metal contamination and essentially no iron contamination. Also, for comparison, we prepared some supports with iron doping or nickel doping. And then we took these materials through the same acetonitrile pyrolysis treatment, and then we purified these materials. We purified the carbon by washing the product with hydrochloric acid. First of all, if we look at the weight gain over these alumina supports, here is the weight of the alumina support, and this is the carbon deposited. So we have close to 20–30% carbon depositing, and these are different support materials with iron, nickel, or without. And after hydrochloric acid washing, we're essentially losing pretty much all of the alumina. But again, especially for example, if you look at nickel, there's probably some of the metal still left behind, because this clearly is more than the green bar, which is due to the deposition of carbon here. If we look at the surface areas, these are the untreated alumina after the acetonitrile pyrolysis. And this is the surface area after the HF washing. And you can clearly see that we are getting very, very high surface areas over these materials which are grown on sol gel alumina, and after pyrolysis of acetonitrile have been washed using hydrochloric acid to get rid of all of the alumina and the metal present. Now, if we look at the X-ray diffraction patterns, these are CNX samples grown on alumina, and this is before the hydrochloric acid washing. We see that these spacings that correspond to the carbon, but we also see these spacings that correspond to alumina, but there's also some nitrided or oxygen deficient alumina as well, and we've seen evidence of this using XPS. But after washing it with hydrochloric acid, what we see is only these spacings, the diffraction lines that correspond to the graphite, and we really don't have any of the alumina left in these samples. Now, we wanted to characterize the natural iron in these materials before we washed it away. And one of the best techniques, of course, for characterizing iron is mass power spectroscopy. And we have an ongoing collaboration with some colleagues at the CNRS Catalysis Research Institute in Lyon, France, where I spent some sabbatical time 12 years ago and also more recently. So we sent Paul to France, which he gladly accepted to go. And he spent a few months there doing some mass power spectroscopy. And if we look at these carbon structures, these are before washing, and characterize the nature of alumina, it is possible to really differentiate. Most of what we see is cementite type carbon iron carbide, but we also see metallic iron and very small amounts of partially oxidized iron. Now, if we look at how the spectrum is changing with the time of the pyrolysis, as you can see, the carbide signal is growing and the paramagnetic iron, metallic iron, is coming down. Mass power spectroscopy was really important because it provided some insight. First of all, it showed that the cementite phase is increasing with the time of acetonitrile pyrolysis, and this really gave us insight about the mechanism of fiber growth through a carbide intermediate. We have done low temperature 77K mass power spectroscopy to verify the nature of the metallic iron as paramagnetic phase, gamma iron, and the nature of the iron particles left in these samples after washing gave us the indication that they could only exist if they are completely encased in graphite. And then also there was no evidence of nitrogen stabilized iron center or any correlation or activity with an existing iron phase. So this really gave us further support that iron is not the active site for the oxygen reduction reaction. Looking at the activity performance of some of these materials, as you can see, these are done using 1000 RPM, so we're really looking at the baseline separation. The particles which are grown on iron-containing alumina takes off much faster, so they have higher activity, and then comes the ones which are grown on alumina, and the worst performance is given by the particles which are grown on nickel-containing alumina. These are after hydrofluoric acid washing. So clearly we're getting significant activity, and again, if the starting material has iron to start with, we get better activity. And if we look at the TEM images, these are carbon structures grown on nickel-containing alumina. You can see multiple carbon, and here are the graphite planes perfectly parallel to the axis of the fiber, so there's essentially no edge plane exposure in these materials. And here's a close-up view of the same catalyst. You can clearly see the basic plane lining up here. If we look at CNX materials grown on iron-containing alumina, again, this is after hydrofluoric acid washing, we see this what we call a stack cup structure. It's a compartmentalized growth, and if you look at closely, the graphite planes are really ending at an angle to the main axis, exposing mostly the edge planes of the graphite. Again, this is a closer look. Pure alumina gives a mixture. In some cases, we see the stack cup structures. We also see some nano onions grown over pure alumina. But if we look at the oxygen reduction reaction activity and how it correlates with the nitrogen content, and especially the pyridinic nitrogen content, we see a very interesting behavior. If we look at, again, deconvoluting the pyridinic nitrogen here, as we go in this direction, we clearly see that the pyridinic nitrogen signal is growing. And this is also the direction where we are getting the increased oxygen reduction reaction activity. So this is very similar to what we have seen over the materials, carbon materials that are grown on water carbon. It's because it's much easier to remove the support. You can use relatively low concentrations of acids or bases, and you can remove the support quite easily compared to aluminum support. And again, if you look at the TEM images, this is fibers grown on pure magnesia. Here is iron-containing magnesia, the CNX samples grown, and again, you can see the stacked up structures. And a closer look, this is cobalt. We have tested cobalt. It's also giving a very good performance of cobalt on magnesia, so CNX fibers grown on this support. Iron on silica, cobalt on silica, and for example, nickel on silica. We don't see any fibers, but we see mostly these onions. So, and this also has very, very poor oxygen reduction reaction activity. Again, if we go back to our correlation and look at the catalysts which are grown on silica support, here's the direction that the pyridinic nitrogen is increasing, and here's also the direction that the oxygen reduction reaction is increasing. So just to quickly summarize, again, as I said earlier, Elizabeth is going to present a poster in the afternoon, and she'll talk more about the more recent work, especially about the potential of these materials as a catalyst for direct methanol fuel cell, which is really looking very promising. So what we have seen is that iron is really acting as a catalyst for the formation of these nitrogen-containing carbon nanostructures, and the activity of these materials in oxygen reduction reaction improves with the increased edge plane exposure. And again, it could be related to pyridinic nitrogen, or pyridinic nitrogen can be a marker for the edge plane exposure. At this point, we don't have a definitive answer, and that's what we're trying to answer at this point. And these CNX materials, these carbon nanostructures, nitrogen-containing carbon nanostructures, have potential as oxygen reduction reaction catalysts in PEM fuel cells. I don't know how I did in time, but let me finish by acknowledging the financial support provided by National Science Foundation, U.S. Department of Energy, Ohio Department of Development through the Wright Central Innovation for Fuel Cells. And of course, I'd like to thank my research group. These are relatively, well, these are somewhat old pictures, probably 3-4 years old. We're enjoying a picnic at our home. And this is a more recent picture of the research group in front of our department in Ohio State. We may be missing a few people, but this is most of the people. With that, I'd like to thank you for giving me the opportunity to talk about this work. And if there are any questions, Elizabeth will answer all of them.
We have time for just a few questions. Yes.
If you compare this catalyst with platinum catalyst, what is the comparative activity?
We're about 100, 120 millivolts away from the platinum catalyst activity. So clearly platinum is still more active. But it is possible to use more of these materials, of course, because cost is not a factor. Whether we will run into mass transfer limitations still is a question we have to answer, because obviously you cannot just keep adding more and more material. But it is showing potential, but it is not as active as the platinum catalyst at this point.
And you mentioned that you determine nitrogen surface area. How do you determine nitrogen surface area?
Nitrogen surface site?
Area.
No, surface area. We looked at the surface area and we looked at the surface composition. And from that, we got the nitrogen surface area.
Total surface.
Total surface area, and we looked at how much of the surface is covered by nitrogen, looking at the XPS signal.
Any other questions? If not, please help me thank Umit one more time. Our next presentation will be by Mark Crocker from the Center for Applied Energy